I welcome all the students for this presentation. This is for both 5th semester regular and parallel scheme students. I start with module 2 and Dr. Sarvasavareddy. In this module 2, you have the impact stress is one part and the fatigue is going to be the another part. There are two sub-chapters you can say. And these two are independent. Impact stress is never connected to fatigue analysis and fatigue analysis is never connected to impact stresses. The general word impact you has already understood, saying that there is a collision of one component with respect to another component. Both may be in motion or one is in motion and another is in stationary. So the impact happens is nothing but impact load is a load that is rapidly applied in case of the machine components. The stresses produced due to this impact load is called as the impact stress. The word what we have here is the impact stress, and that impact stress is caused because of the impact load. Now let us say in the machine members we have this kind of loads happens in case of the machine components like the hoisting machines. You can see hoisting ropes, hammers. When you hammer to anvil or when you hammer to other component for obtaining the forging and other things, then it is going to have an impact. Springs are subjected to impact because if you say simple example of a calling bell in the residential houses, when you press with a thumb, there is a spring inside which makes electrical contact, so you are applying a sudden load. So that is called as a springs, impact stress. You have also in case of the punches, you have shears, clutches and brakes. So these are the examples where you have the component subjected to impact loading. Now let us consider here an object or whatever is called as an elastic body. So this is an elastic body which I written as A, having a cross section area as A, impact elastic body attached at one end. So this end is fixed. At the other end you have a collar. Here you can see a disc-like structure what you have is called as a collar. This member, elastic member, is having a length as a L. On this member I have a load here which I have shown by hatched line. This is called as the impact load W. This is going to freely fall from a height as h. So this load falls freely from a height h and it impacts this collar. Okay, suddenly this moving load comes and hits the collar which is stationary. As a result, this is elastic material. This will move down by this much of this. The dotted line whatever I have shown here is the deformation. So this member will move by a deformation as y. Therefore, here this load W is going to lose energy which is called the potential energy. It falls from the height. So it is going to lose energy as a potential energy. Potential energy is nothing but a load into total distance traveled. Total distance traveled is h plus this y. So when it moves to distance h and y together to come at this particular position. So the potential energy lost by the falling weight is W into h plus y. Meanwhile, this elastic member is going to absorb that energy. So that is half P into y. So every is load into displacement. That displacement is nothing but y. So therefore I have here equations. So this is the case of what we call as axial impact load, free falling load due to axial. I have underlined here as the axial load case. There is also bending load case. There is a torsion load case. Three different cases are there in this. Now the configuration whatever I have shown here, this is a case of axial load. So this load is moves parallel to axis of this elastic member. Therefore, this is called as the axial load case. So here the potential energy lost by the falling weight is W into h plus y. H plus y is the total distance travelled by the falling weight. So weight into distance travelled is going to give me potential energy lost by the falling weight. Meanwhile, the member is going to store the strain energy in the bar, that is half into P into Y. Half P is nothing but the average load into displacement. So I am going to equate these two. So when I equate these two for equilibrium, half P into Y, this is energy stored by the member equated to energy lost by the falling weight. Where W is the falling weight and P is the equivalent amount of load saved in the member. This is a U. So next what I do is a simple thermodynamic, what you call equilibrium equations for the stability or for the equilibrium. So next I go for replacing this P and replace Y by means of the basic definitions. What is the basic definition? Stress is going to be equal to load divided by A. From that, load is going to be stress into A. Basic definition. Only thing that stress I load as a sigma dash, where sigma dash is going to be called as impact stress. Then I have a strain definition as studied in the third semester mechanics of material. Change in length by original length. So that is called as a strain. Also by the Hooke's law, stress by Young's modulus is going to be the strain. Strain is by the basic definition, change in length by original length. By the Hooke's law, strain is nothing but the stress divided by Young's modulus. So the stress I designate as a sigma dash. So from these two equalities, deformation Y I can calculate sigma dash into L by E. So this value of Y and this value of P, both I substitute here, P and Y as well as this Y here. When I substitute and rearrange for the terms, I get as sigma dash squared into AL by 2E minus sigma dash into WL by E minus W into H is equal to 0. So this is after rearranging the terms containing sigma dash square and sigma dash terms. Then I multiply throughout entire this equation by the reverse of this term, 2E by AL, that is the reverse. Okay, so I have written here, multiply throughout by 2E by AL, that is the component of sigma dash square reverse. Okay, so when I do that, I will get a term as a sigma dash square minus 2 into W by A sigma dash minus 2 EH by L into W by A is equal to 0. So if you see this equation, it is the equation of the term of the right x square minus something x minus constant is equal to 0. So this is going to be a quadratic equation which has highest roots. So root, if I get a positive highest root, sigma dash is 2 W by A, minus of minus it becomes a plus, square root of W by 2 W by A whole square, then minus 4 AC, so minus of minus again plus 4 2 AEH by L into W by A whole divided by 2. Then what I do is I take a 2 constant outside, 2 from here, 2 from here, 2 from here, and divide that by 2 here in the denominator. Then I take W by A also constant outside throughout in the numerator. So I will get a sigma dash is equal to W by A constant outside into. So 2 has cancelled, 1 W by A is gone outside, only left is 1. 1 plus square root of, similarly here also 1 is left, plus 2 AEH by WL remains. So this equation is going to be the final equation to calculate the impact stress based on the instantaneous load applied, area of the elastic member and height of fall and its material properties and the length of the elastic member. So if I know all these parameters, I can easily calculate the impact stress induced in the elastic member or in the axial member subjected to axial load W. Okay. So this equation for impact stress is available in the design letter handbook, in the Belvedere-Madhavan book as well as in the HE book. So in Belvedere-Madhavan book, in page number 27 and 28, you find these kind of equations along with the diagram. So you find this diagram is available and the final equation. So this equation which I written in the bracket here is also available. So students may be asked in the examination to derive this equation. If you are asked to derive the equation, figure is available, final equation is available. Your duty is to write some statements of this example and from the equilibrium equations arrive at the final equation. Therefore, it is easy for students to do this derivation. And once this equation is known, we can easily solve the examples based on this equation. Equation is finally available. Okay, so that's it. And then we have some remark based on this equation. This equation is the equation for impact stress for axial loaded member. Suppose in this equation, if this h, height of fall, is going to be 0, I written if s is 0, what happens if s is 0? So this second term becomes 0. So square root of 1 is 1, so 1 plus 1 is 2, so 2 times W by A remains. That's what I have written here. Sigma dash is 2 times W by A. So that W by A is nothing but stress. So 2 times stress. Where this stress sigma is going to be static stress, which is load by area as a definition concerned W by A. So this is equation. Which means that instantaneous stress is 2 times the static stress. So it is an approximate equation to calculate the instantaneous stress as a 2 times the permissible stress. So static stress we know for the material. So static stress is nothing but the yield point stress by factor of safety, that is going to give me static stress. So when I know the material, I can calculate the static stress. So 2 times that it will give me impact stress. It's a rough calculation. But when the impact load is applied, all details are given. This is the exact equation to calculate the instantaneous stress. Then the deflection, y is going to be, as I know, sigma by E into L. Sigma, if I replace here, is a W by A, L by E. So it is similar to the deflection or deformation equation in the mechanics of metal third semester, which is divided as a P into L by A into E. Okay, instead of P, I have written W here. This is nothing but axial deflection. So therefore, this equation, W by A is a static stress, is nothing but sigma here. And this AE in the numerator, you take to the denominator of this denominator, so it becomes here WL by AE. So WL by AE is Y. So I can rewrite that as a 2H by Y here. Same equation, whatever there here, W by A I have replaced by sigma. WL by AE, which is available here, I replaced it by Y, that's available here. So this is also an important equation to calculate the stress sigma dash directly based on this parameter. So either you remember this equation or you remember this equation. So both these equations, this as well as this equation, are available in the data handbook. Since stresses and deflection are directly proportional, so I can write down, I can replace sigma by y, so it is y dash is equal to sigma by y into 1 plus square root of 1 plus 2h by y. Where this y is static deflection, y dash is instantaneous deflection. So in the figure whatever I have written here, y, so this is nothing but a y dash. This is instantaneous deflection y dash. So these are all the equations concerned to the axial deflections. Now I will go for same equation with respect to impact stress due to bending. So I have example of a cantilever beam here, fixed at one end, having a length as well. At the free end, instead of writing a load by arrow down here, I write as a load W, which falls freely from a height h. As a result, this cantilever bends down, deflects to the dotted line, whatever I have shown. So it will move by a distance as y. So this is a distance y. This is nothing but instantaneous deflection. So same equation I will rewrite here. Sigma dash instantaneous stress, sigma dash is sigma into 1 plus square root of 1 plus 2h by y. So this is also a same equation applicable for cantilever beam or otherwise for the bending. So this is for the bending stress analysis. But the term way in which this sigma and y to be calculated are different. So sigma in the case of axial load is going to be W by A and y is going to be WL by A, but here it's a different. Sigma is a static bending stress, that is M by Z. So I have to use a pure bending moment equation here, so that's M by Z. And y is a deflection due to bending load. So when you apply a load here, so this beam is going to bend down like this, so this y is going to be deflection due to this bending load. So that you have to calculate based on the type of beam you are given with. So this beam F into L cube by 3EI. So this is in case if it is going to be cantilever beam. So FL cube by 3EI if it is going to be cantilever beam. Okay. It is going to be FL cube by 48 EI in case it is going to be simply supported beam with a point load at the center. So these two equations are also available as data handbook in the different table. Otherwise you got to remember. Where this F is same as W which is applied at the end of the cantilever beam or at the middle of the simply supported beam. L is length of the beam, E is the material property of the beam, I is the moment of inertia which depends on the cross section of the beam. So once I know this equation, I can calculate deflection value. So this sigma is from the pure bending moment equation M by Z. So I can calculate sigma by this equation. I can calculate this y by either this equation or this equation and substitute here. So I will get instantaneous bending stress sigma B dash. Similarly, I can calculate impact stress due to torsion. So when there is a torsional instantaneous stress, we can calculate tau dash. Tau is a notation for shear stress. When a torque is applied, shear stress is induced, tau dash. That is going to be tau into 1 plus square root of 1 plus 2h by r theta. So this is r is the radius of the shaft, theta is angle of twist which is undergone. So by means of this equation also you can calculate the torsional impact shear stress. So these are the three equations what we have. I repeat again. This is the equation concerned to instantaneous axial loaded member. Then this is the equation concerned to the instantaneous bending loaded member. Then this is the equation concerned to the twisting moment load, instantaneous shear stress. Three equations are there. And all these equations whatever discussed are available in the designer handbook. You have to see the example, whether examples are given to you for axial load case or a bending load case or a torsion load case. Then use appropriate equation. Equations are available in the data handbook. Okay. So page number 27 and page number 28 of Madhavan Belvedere data handbook, you find these equations. Similarly, in HC portal also you find these equations. I do not know the page number. Students are required to find out which page number. So based on this, the uttermost derivation for the axial load case, whatever I discussed here earlier for the very first case, this axial load case may be asked for derivation. You are required to remember the derivation. Okay, practice the derivation. Then based on these equations which are available to us, I directly go for some few examples in the first session class. The first example, simple example I read here. A weight of 1400 Newton is dropped onto a collar at the lower end of the vertical steel shaft of 3 meter long and 25 millimeter diameter. So this is a description about the vertical member. Calculate the height of drop if the maximum instantaneous stress induced or produced is not to exceed 120 megapascal. So he has given you the instantaneous stress already. Take the material property like Young's modulus E as a 2.1 into 10 to the power of 5 megapascal. So this material properties are available for the steel shaft or steel material in the data handbook. So if this is not given, there is a student's duty to find out the material property E for steel material and then continue the example. So every data may not be given to you sometimes. So first what is going to be important here is, first example you have to identify whether it is a vertically loaded member or a bending load or a twist. So you have given here a weight which is being dropped onto a collar at the lower end of the vertical shaft. So it's the first case where you have the instantaneous load being applied onto the vertical member, which is going to be axially loaded impact load. So the first type of equation what we have, instantaneous stress is sigma dash is W by A into 1 plus square root of 1 plus 2 AEH by WL. This is the equation what is available to you. So in this you substitute all data. What is a straightforward example. So instantaneous stress on the left hand side Sigma dash is already given in the example. Load is given in the example. Pi of 4 d square, diameter of the steel rod is given. Then 1 plus square root of 1 plus 2, this is area. Pi of 4 d square area is given. H is you are required to calculate. And then the W is given and L is given. So you have to simplify this. All terms are given. You have to simplify this and then calculate the value of H. For simplification, what you can do, you apply the square on both sides. You square on this side, square on this side, the square root will go up. Then transfer the terms, you will get the value of H. So I have directly written the value of H here. Students are required to practice how the simplification is going to happen. Then you will get the value of H. The height of fall, you will get 34.26 mm. Okay. I have another example. A camshaft of 25 mm diameter is mounted on a ball bearings 250 mm apart. It carries a cam midway between the bearings. The follower weighing 1.5 kN is out of adjustment so that impact is produced when contacted by the cam. The height of fall is estimated as 0.3 mm. You can see height of fall is very, very less. If the shaft is made of SAE 1045 annealed steel, it is a steel material, determine the maximum bending stress induced in the shaft. So this is going to be a camshaft mounted between the bearings, and height is, and the load is falling at the mid. That means it is going to be a bending load, instantaneous bending load example. So a rough diagram I have written here. This is a shaft, 250 mm length between the bearings. So this is a cross mark is one bearing on this side, cross mark is another bearing on this side. 1.5 kN is a load applied instantaneously from a height of 0.3 mm. This height of fall is 0.3 mm. And it is applied at the middle. So it is a bending case, instantaneous bending. So impact bending stress sigma dash is sigma into 1 plus square root of 1 plus 2h by y. So static bending stress sigma is m by z. Let me calculate this term sigma and y separately first. So bending stress I calculate m by z. M is a bending moment. So what is a bending moment? If a simply supported beam at the point load at the center, bending moment is FL by 4, which is studied in the third semester mechanical materials subject. I should know this. Otherwise, in the data handbook, we find this also. And Z is a section modulus as I by Y. So pi by 32 d cube. So when I know this equation, this is also available in the data handbook. Substitute the values here and simplify, you will get the bending stress. This is static bending stress. Then similarly, y I calculate is static load. So that is going to be FL cube by 48 EN, because these are simply supported beam with a point load at the center. So for that bending deflection equation is this. So all values are substituted here. So here E is Young's modulus for the material, steel material 2.1 10 raised to 5, which is not given in the example. You can see it's not given. So therefore I am going to assume, we are given with the SAE 1045 annual steel material. So Young's modulus for the steel material, I am going to assume 2.1 10 raised to 5 megapascal or Newton per mm square. I have not written anywhere as a statement, I am assuming. But your duty to write it as assuming Young's modulus is 2.1 10 raised to 5 megapascal for steel material. Then only you make a substitution here. Then when you simplify that, you will get this y value. Okay. So now sigma and y value you substitute in this equation. That is what I have done here. It's a sigma value here and y value here. That is 2, h is given as 0.3. Simplify this, you will get as a sigma dash 210.196 megapascal. That's in fact instantaneous. Student can make a remark based on this values. Instantaneous stress is 410, whereas static bending stress is 61 megapascal roughly. For the same load, you calculate a static bending stress and instantaneous. So instantaneous stress you find is very much higher value. So therefore, whenever such members are subjected to instantaneous stress, the designer must be very, very careful to design the member for this value rather than this value. If you design the member for this value, if impact loading is going to come, then the metal is going to fail. So rather you have to design such kind of member for this kind of stress, not as an instantaneous stress.